Good morning everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about soap film analogy, its concept and applications for deriving the torsional constant J. So, we discussed in the last class the behavior of members under torsional moment. We talked about circular cross-sections and we understand that circular cross-sections remain circle even after the application of the torsional load, and the deformations are within the cross-sections, which is U and V. And the torsional constant J is equal to the polar moment of inertia. However, for non-circular cross-sections, the undeformed as well as the deformed cross-sections shown in the picture indicate that in addition to twist, which is defined as rigid rotation of cross-section about longitudinal axis, the cross-section will also experience what is known as warping. Basically, warping is an axial deformation of the member due to application of torsion. So, warping is basically the longitudinal or axial deformation of the cross-section. Pictorially, it is shown above. And here, the plane of the cross-sections do not remain the same. The out-of-plane deformations are observed in non-circular cross-sections, especially in W. U and V are there, but in W, which is the out-of-plane deformation. And the torsional constant J is not equal to the polar moment of inertia. So, in circular sections, T equal to Gj theta. So, here in non-circular cross-sections, T equal to 2 into double integral of phi into dx into dy as given above. The crux of the question is how to find J. In non-circular cross-sections, the value of T is equated to G, theta and J. So, a good approximation of phi is required to find J. Now, the J can be determined using the Prandtl stress function phi. So, the stress function phi is specific to cross-section. We can use a direct method which requires special methods and not the scope of this course. The other method that we can use here is the indirect method. We will understand the selection of phi for certain types of cross-sections. So, the indirect method, phi equal to b into f of x comma y. Here b is a constant. F of x comma y represents the boundary of the cross-section of torsion member. And this is given for a elliptical cross-section where phi equal to b into x square by h square plus y square by b square minus 1. Here phi can also be derived for a triangular cross-sections whose equation is given above, which is much more complex than the elliptical equation. However, for practical cross-sections such as I-sections and box sections, it is difficult to obtain analytical formulations for phi, and we need to use approximate solutions for obtaining phi using what is known as Prandtl's membrane analogy. It is also known as soap film analogy. Now, the Prandtl's membrane analogy can be considered by looking at a cross-section. So, let us consider an opening in xy plane. What you see here is the plan view, and the front side view is given here as well as the side view. So, assume it to be covered with a homogeneous elastic membrane, and the deformed shape of the membrane can be seen in the front view as well as the side view. The applied pressure P is the internal pressure. So, upon application of an internal pressure P, the membrane deforms as shown in the figure above. So, consider a small element ABCD of dimensions dx and dy of the elastic membrane. S is the surface tension, which is defined as the force per unit length developed in the membrane along the edges AB, BC, AB and DC. Now, the surface tension is given in this figure here. For the front view, where it is defined as alpha for the left hand side with a small increment on the edge BC, it is alpha plus dou alpha by dou x into dx. Similarly, for the side view, it is defined as S on the left hand side, which is for edge DC, and then for the edge AB, it is basically alpha plus dou alpha by dou y into dy. So, now let us determine the force components of the surface tension S. So, for edge AD, it makes an angle alpha, the surface tension, whose components can be resolved as S into dy into cos alpha in the horizontal direction and S into dy into sin alpha in the vertical direction. So, the net vertical force is equal to minus S dy into sin alpha. Because dy is pointing downwards, it is taken as negative. So, for small values of alpha, sin alpha is equal to tan alpha. So, this becomes minus S dy into tan alpha. Tan alpha from the front view is defined as tan alpha equal to dou z by dou x, which is equal to minus S into dy into dou z by dou x. Similarly, for edge BC, we have the following resolution as you can see here. Here, instead of alpha, we have alpha plus dou alpha by dou x into dx, and it makes an angle of alpha plus dou alpha by dou x into dx with the horizontal, and it makes an angle of sine of alpha plus dou alpha by dou x into dx with the vertical. So the net vertical force here is S into dy into sine of alpha plus dou alpha by dou x into dx. For small values of alpha, sin alpha equal to tan alpha. So it becomes S into dy into tan alpha plus dou alpha by dou x into dx. From the front view, we also know that tan of alpha plus dou alpha by dou x into dx is equal to tan of z plus dou z by dou x into dx. So this becomes S into dy into dou by dou x of z plus dou z by dou x into dx. So now let's look at the side view. So for edge DC to begin with, we have an angle of alpha that it makes with the horizontal one. Here we have to look into horizontal as the one that is pointing downwards because the vertical is always out of the plane. So when you look at it, S into dx into sine alpha is the vertical component. So the net vertical force equal to S into dx into sine of minus alpha because it is counterclockwise is taken as positive and clockwise is taken as negative here. So it becomes minus alpha. So that becomes minus S into dx into sine alpha. For small values of alpha, sine alpha equal to tan alpha, which becomes minus S into dx into tan alpha. From the side view, we know that tan alpha equal to dou z by dou y. So it becomes minus S into dx into dou z by dou y. Similarly, for edge AB, we have an increment in alpha. So alpha becomes alpha plus dou alpha by dou y. So the resolution is shown on the right hand side picture here. So the net vertical force equal to minus S into dx into sine of minus of alpha plus dou alpha by dou y into dy. Here, there are two minus signs. The minus sign outside is because it is acting in the direction opposite to the vertical direction. So S dx into sine of alpha plus dou alpha by dou y into dy is acting opposite because it is not pointing upwards. It is pointing to the right side. So it becomes minus. The minus inside the bracket is simply because of the sign convention. Hence, we have this equation. Net vertical force is equal to S into dx into sine of alpha plus dou alpha by dou y into dy. So for small values of alpha, again sin alpha equal to tan alpha. This becomes S into dx into tan of alpha plus dou alpha by dou y into dy. From the side view, we have tan of alpha plus dou alpha by dou x into dx is equal to tan of z plus dou z by dou x into dx. So this becomes the net vertical force equal to S into dx into dou by dou y of z plus dou z by dou y into dy. Now the force components along the z direction is given for edge AD, edge BC, edge DC as well as edge AB. Now let's sum the equilibrium of forces along the vertical direction z axis. So the total applied force due to the surface tension T is equal to P into dx into dy along the z axis. The summation of the forces is equal to 0. So minus S into dy into dou z by dou x plus S into dy into dou by dou x of z plus dou z by dou x into dx minus S into dx into dou z by dou y plus S into dx into dou by dou y of z plus dou z by dou y into dy plus dx into dy, which is the internal applied force equal to 0. So when we expand it, we will see that there are terms that can be easily cancelled. As you can see, the first two terms can be cancelled. Similarly, the fourth and the fifth term can also be cancelled. So now we have S into dx into dy into dou square z by dou x square plus S into dx into dy into dou square z by dou y square plus P into dx dy equal to 0. We can take S into dx into dy common. So we have this S into dx into dy into dou square z by dou x square plus dou square z by dou y square is equal to minus P into dx dy. Again, we can cancel dx and dy. We get dou square z by dou x square plus dou square z by dou y square equal to minus P by S. So using the non-zero stress components, basically sigma zy and sigma zx from the previous derivation that we saw in the last class, we know that sigma zx equal to dou phi by dou y, which is equal to g into gamma zx, which implies dou phi by dou y equal to g into gamma zx, which means that gamma zx equal to 1 by g into dou phi by dou y. Similarly, dou z by dou y is equal to minus dou phi by dou x, which is equal to g into gamma zy, which implies minus dou phi by dou x equal to g into gamma of zy, which gives the equation gamma zy equal to minus 1 by g into dou phi by dou x. So substituting these values in equation 3, which is the equation in the previous derivation, we have dou of gamma zx by dou y minus dou of gamma zy by dou x is equal to minus 2 theta. So when we substitute that, we have dou by dou y into 1 by g into dou phi by dou y minus dou by dou x of bracket open minus 1 by g into dou phi by dou x is equal to minus 2 theta. So this again boils down to dou square phi by dou x square plus dou square phi by dou y square is equal to minus 2 g theta. Because the g goes to the other side, it becomes minus 2 g theta. So we can see that these two equations are quite analogous. So this is an equivalent expression from elasticity method. So now analogous terms from these equations, the out of plane deformation function of membrane Z can be represented as C into phi, where C is the constant of proportionality. So when we substitute Z equal to C into phi, we have dou square C phi by dou x square plus dou square C phi by dou y square equal to minus P by S. We can take C common outside. So C into dou square phi by dou x square plus dou square phi by dou y square equal to minus P by S. So we get here C into minus 2 g theta. So basically we are substituting dou square phi by dou x square plus dou square phi by dou y square equal to minus 2 g theta given on the right hand side of the page. We are substituting that here. So we get C into minus 2 g theta equal to minus P by S. So this indicates minus P by S equal to minus C 2 g theta, where C is the constant of proportionality. This equation will be helpful in the coming slides, which you will see very shortly. Now let's look at the torsional constant J and how to derive J for a narrow rectangular cross section. So let us consider a narrow rectangular cross section of width 2h and depth 2b, as you can see from the right hand side. So by following the Prandtl's membrane analogy, if the cross section is covered with an elastic membrane and subjected to an internal pressure P, the membrane starts to deform as shown in the figure on the right hand side. Since the deformed shape is symmetric, the stress function phi must be even in both x and y. So further, the stress function must be defined by two conditions, which is del square phi is equal to minus 2 g theta over the cross section, where del square equal to dou square by dou x square plus dou square by dou y square, which is understood, and then phi equal to 0, which is the stress potential around the perimeter. So the total stress function phi is considered as a summation of two parts. Number one, assuming phi is independent of y. Number two, assuming an even function v in x and y. It may look little tedious right now, but once you go through the mathematics, I'm sure that you'll appreciate the derivation part as well as how the mechanics that is being derived is directly relevant to the equations present in IS 800. So for the time being, I request you to be little more patient. Please follow the derivation and then you will appreciate and understand the importance of the mathematical derivations, which are going to come in the next few slides. So for first part, using Prandtl's membrane analogy, assuming that the membrane deflection Z is equivalent to the stress function phi, where C is a constant. This equation was already seen in the previous slide. Now we have Z equal to Z naught into 1 minus x by h the whole square. This is basically a parabolic equation, and here 1 minus x by h square denotes the shape and Z naught denotes the magnitude, as you can see from the right hand side of the picture. So from Prandtl's membrane analogy, the membrane deflection can be defined as dou square Z by dou x square plus dou square Z by dou y square equal to minus P by S, which we have seen in the previous slide. The left hand side of the equation is dou square Z by dou x square plus dou square Z by dou y square. Here, since it is a partial differentiation, the value of y will be 0 because Z does not contain the terms of y. So it only contains the terms of x. It has minus x by h square, which when we differentiate first time it becomes minus 2x, the next time it becomes minus 2. So the value here boils down to Z naught into minus 2 by h square, which is equation 1. So we also know that dou square Z by dou x square plus dou square Z by dou y square equal to minus P by S, but minus P by S is also equal to minus 2c g theta from the previous derivation. So when we substitute that, we can also cancel the two values here. So this becomes Z naught equal to ch square g theta, where Z naught is the amplitude of the displacement of the membrane. So substituting Z equal to Z naught into 1 minus h by x square, we have C phi equal to ch square into g theta into 1 minus x by h the whole square. Again, we can cancel the c on both sides. We get the stress potential phi equal to h square into g theta into 1 minus h by x the whole square. So when we further simplify it, we will get that the h square term can be cancelled when we take the LCM. So phi becomes g theta into h square minus x square. So for the second part, let us consider an even function v of x comma y. So the total stress function is given as phi equal to g theta into h square minus x square plus v of x comma y. So finding the even function v of x comma y. So substituting the total stress function phi into two conditions. The condition 1 is del square phi equal to minus 2 g theta over the cross section and phi equal to 0 around the perimeter. So these two conditions must be satisfied by the stress function phi. So substituting the value of phi into condition 1, we have dou square phi plus 2 g theta equal to 0. So basically we are taking this minus 2 g theta on the right hand side to the left hand side. It becomes del square phi plus 2 g theta is equal to 0. So it becomes dou square phi by dou x square plus dou square phi by dou y square plus 2 g theta is equal to 0. So when we do so again, we know that this dou square phi by dou x square is a partial derivative. So we have only g theta into h square minus x square plus v of x comma y plus dou square by dou y square into g theta into h square minus x square plus v of x comma y plus 2 g theta is equal to 0. So we will do so, and when we do the differentiation, we get the first term as minus 2 g theta plus dou square by dou y square into v of x comma y. In the second term, we have dou square by dou y square into v of x comma y, because when we partially differentiate the term g theta into h square minus x square with respect to y, it becomes 0, and hence this equation. So again we can cancel minus 2 g theta and plus 2 g theta. So this becomes dou square by dou x square into v of x comma y plus dou square by dou y square into v of x comma y is equal to 0. So this means that del square v equals 0 over the cross section. So the first boundary condition actually is satisfied. So substituting the value of phi into condition 2, which is phi equal to 0 around the perimeter, for x equal to plus or minus h, which is the perimeter, we have g theta into h square minus x square plus v of x comma y is equal to 0. So this means that when we substitute x equal to plus or minus h, we have g theta into h square minus h square plus v of x comma y is equal to 0. So we have this first term equal to 0. So v of x comma y is equal to 0. So this is one side of the boundary. The other side of the boundary, for y equal to plus or minus b, we have g theta into h square minus x square plus v of x comma y equal to 0. So which means that since the term does not contain the values of y, v of x comma y is equal to minus g theta into h square minus x square for y equal to plus or minus b. So we can further simplify this by taking the negative side inside. So we have v of x comma y equal to g theta into x square minus h square. So now v of x comma y can be represented as 0 for x equal to plus or minus h, which becomes equation 3, and is equal to g theta into x square minus h square for y equal to plus or minus b for equation 4. So now let's use the method of separation of variables. Now let us assume v of x comma y equal to f of x into g of y. So substituting v in equation 2, we have del square v equal to 0. So we have dou square by dou x square plus dou square by dou y square into v of x comma y equal to 0. So now we have dou square by dou x square plus dou square by dou y square into f of x into g of y is equal to 0. So g of y into dou square f of x by dou x square plus f of x into dou square into g of y by dou y square is equal to 0. We can simplify this further by substituting f double dash for dou square f of x by dou x square and g double dash for dou square g of y by dou y square. Now we get g into f double dash plus f into g double dash is equal to 0. So this becomes g f double dash equal to minus f into g double dash. So this can be further simplified as f double dash by f equal to minus g double dash by g equal to minus lambda square. Now here minus lambda square is a multiplier which satisfies the equation g f double dash equal to minus f g double dash. So using this one, we have two equations, f double dash plus lambda square f equal to 0 and g double dash minus lambda square g is equal to 0. So this can be represented as d of x plus lambda square into f equal to 0 and d of y minus lambda square into g equal to 0, where the d represents the double differentiation. The roots of the characteristic equation for d of x plus lambda square equal to 0 is d of x equal to plus or minus lambda I. So for the next one, d of y minus lambda square equal to 0, we have dy is equal to plus or minus lambda. For general solution for f comma g, we have for complex roots, that is for alpha plus or minus beta I, we have e power alpha x into a cos beta x plus b sin beta x, which means that f equal to e power 0x into a cos lambda x plus b sin lambda x. For real and distinct roots, that is plus or minus alpha, we have a into e power alpha x plus b into e power minus alpha x. So g becomes c into e power lambda y plus d into e power minus lambda y. Now let us simplify these values further. So this g can be further simplified by adding and subtracting e power minus lambda y by 2 and e power plus lambda y by 2 to the terms c and d in the g equation, g equal to c into e power lambda y plus d into e power minus lambda y respectively. So what happens? So we have g equal to c into e power lambda y by 2 plus e power lambda y by 2. Both of them are basically, when we add them together, we have e power lambda y. So this is basically splitting e power lambda y as e power lambda y by 2 plus e power lambda y by 2. The third term is e power minus lambda y by 2, and then we subtract e power minus lambda y by 2, basically adding and subtracting e power minus lambda y by 2. This is to simplify in terms of hyperbolic functions, which you will come across very shortly. The next is plus d into, again we are splitting this e power minus lambda by y by 2 into 2 halves. So it becomes e power minus lambda y by 2 plus e power minus lambda y by 2 plus e power lambda y by 2 minus e power lambda y by 2. Here we are adding and subtracting e power lambda y by 2. Can again be further simplified, making sure that it is all being able to be represented in the form of a hyperbolic function. We know that cos hy equal to e power y plus e power minus y by 2 and sin hy equal to e power y minus e power minus y by 2. So when we substitute that in this equation, we have g equal to c into cos h lambda y plus sin h lambda y plus d into cos h lambda y minus sin h lambda y. So when we expand this further, we have g equal to c cos h lambda y plus c sin h lambda y plus d into cos h lambda y minus d into sin h lambda y. This again can be further simplified as g equal to c plus d into cos h lambda y plus c minus d into sin h lambda y. This can be given as constant c plus d equal to e and c minus d equal to f, which becomes g equal to e cos h lambda y plus f into sin h lambda y. So therefore, the equation v is v equal to a cos lambda x plus b sin lambda x, which comes from the first equation. The second equation is e into cos h lambda y plus f into sin h lambda y. So now when we expand this equation, we have 4 terms. Okay, but we also know that the sin lambda x is an odd function and cos lambda x, sin h lambda y and cos h lambda y are even functions. So when we multiply an odd function with an even function, it becomes an odd function. So we have 3 terms which are odd functions, and the only term, the first term, ae into cos lambda x into cos h lambda y, is an even function, as you can see. And our focus is simply an even function because the displaced shape of the membrane exhibits an even function. So we are going to disregard the second, third and fourth terms, and we are going to focus only on the first term. So now we have v equal to a sin lambda x into cos h lambda y. So substituting the value of v in equation 3, that is for x equal to plus or minus h, which implies v equal to 0, we have a cos lambda x into cos h lambda y is equal to 0. Here a can be 0, but if a equal to 0, it leads to a trivial solution because v will become 0. Here cos lambda x should be equal to 0 for a non-trivial solution. When cos lambda x is equal to 0, lambda becomes n pi by 2h for n equal to 1, 3 and 5. So lambda is given as n pi by 2h for n equal to 1, 3 and 5. These are the values for which the cos lambda x will be 0. Now substituting the value of lambda into v of x comma y, given as a cos lambda x into cos h lambda y. So this becomes sigma of n equal to 1, 3, 5 up to infinity a cos n pi x by 2h into cos h n pi y by 2h. So substituting the value of b in equation 4, that is for y equal to plus or minus b, v of x comma y is equal to g theta into x square minus h square. So this is something that we derived in the previous slides. So this gives the value v of x comma y is equal to sigma n equal to 135 up to infinity a cos n pi x by 2h into cos h n pi y by 2h. So when we do so, we substitute on the left hand side g theta into x square minus h square is equal to sigma of n equal to 135 up to infinity a cos n pi x by 2h into cos h n pi y by 2h. So we can further simplify this for n equal to 1 and 3. We have this expanded equation g theta into x square minus h square is equal to a cos pi by 2h into x into cos h pi by 2h into y plus a into cos 3 pi by 2h into x into cos h 3 pi by 2h into y plus, and it goes on. So the value here a appears to be constant in this equation, but however when we plot it, we can see that the amplitude of a can be varying. For n equal to 1, as you can see from here, it is a very mild variation. The amplitude is not much. For n equal to 2, the orange color one, there is a variation. But then for n equal to 3, there is a drastic variation in the amplitude. So which indicates that a cannot be a constant. A should also be a function of the series. So now a cannot be a constant. So v equal to sigma n equal to 135 up to infinity a n into cos n pi x by 2h into cos h n pi y by 2h. Hence, we shall use the method of superposition and approximate v of x comma y as a series function. Now v is given as sigma n equal to 135 up to infinity a n cos n pi x by 2h into cos h n pi y by 2h. Let's quickly check if v satisfies the conditions. The condition 1 is del square v equal to 0. And number 2 is that for x equal to plus or minus h, v should be equal to 0. For the third condition, y equal to plus or minus b, v equal to g theta into x square minus h square. So the first boundary condition is del square v equal to 0. So when we double differentiate that with respect to x, which is a partial derivative, we can see that the first term contains cos n pi x by 2h and the second term contains cos h n pi y by 2h. These are the two terms that will get differentiated due to partial differentiation. So when we double differentiate with respect to x, cos becomes minus sign, and then one more time when we differentiate it, we get a negative term. And when the negative term is added to the next term here, it becomes 0. So we have del square v equal to 0. So for x equal to plus or minus h, v equal to 0. So v equal to, given as this equation, sigma n equal to 135 up to infinity a n cos n pi x by 2h into cos h n pi y by 2h. So substituting x equal to plus or minus h, we have a n into cos n pi plus or minus h by 2h into cos h n pi y by 2h. We know that n pi by 2 or pi by 2 of cos is basically 0. So when we substitute it, the first term becomes 0. Hence, for values of n equal to 1, 3 and 5, cos n pi h by 2h gives rise to the value of 0. So the second boundary condition is also satisfied. So for the third one, for y equal to plus or minus b, v equal to g theta into x square minus h square. So when we substitute that, we have the equation on the left hand side, which is given as sigma n equal to 135 up to infinity a n cos n pi x by 2h into cos h n pi y by 2h equal to g theta into x square minus h square. So when we substitute the value of b, we get the following equation. We can further simplify this equation by substituting c sub n equal to a n into cos h n pi b by 2h. So we get sigma n equal to 135 up to infinity cn into cos n pi x by 2h equal to g theta into x square minus h square. Right? Now let's multiply the both sides with cos n pi x by 2h and integrate between limits minus h to plus h. So when we do so, we have integral of minus h to h cn into cos square n pi x by 2h into dx equal to minus h to h g theta into x square minus h square into cos n pi x by 2h into dx. Right? We also know that cos 2 theta equal to 2 cos square theta minus 1. So cos square theta equal to 1 plus cos 2 theta by 2. This is from our basic high school mathematics. So we can substitute that. For that, we have one, instead of cos square n pi x by 2h, we have 1 plus cos n pi x by h by 2. So expanding the previous equation, we have 2 into 0 to h cn into 1 plus cos n pi x by h by 2 into dx is equal to 2 into integral of 0 to h g theta x square into cos n pi x by 2h into dx minus 2 into 0 to h g theta h square into cos n pi x by 2h into dx, which becomes equation 5. Now the LHS of the equation is 2 into 0 to h cn into 1 plus cos n pi x by h by 2 into dx, which is equal to 0 to h into Cn plus cos n pi x by h into dx. So this becomes Cn into x plus h by n pi into sin n pi x by h. The lower limit is h equals 0, the upper limit is h equal h. When we do so, we have Cn into h minus 0 plus h by n pi into sin n pi h by h minus h by n pi into sin n pi 0 by h. So both these terms are 0 because sin n pi is 0 as well as sin of 0 is 0. So this gives us the value LH is equal to Cn into h. So the first term in RH is given as 2 into 0 to h g theta x square into cos n pi x by 2h into dx. So this can be evaluated using the UV rule. So UdV equal to UV minus integral of VdU. So we have U equal to x square, dV equal to cos n pi x by 2h into dx. So du equal to 2x and v equal to 2h by n pi into sin n pi x by 2h. So when we substitute that, we get the above equation here, and the limits are applied x equal to 0 to x equal to h. When we further simplify it, the second term or the lower limit actually is 0, and then we have 4g theta into h cube by n pi minus 4g theta into 0 to h x into 2h by n pi into sin n pi x by 2h into dx. So again, we have the small integral here. This again can also be solved using the UV rule. UdV equal to UV minus integral of VdU. This time U equal to x and dV equal to sin n pi x by 2h into dx. So du equal to dx, v equal to minus 2h by n pi into cos n pi x by 2h. When we substitute that, we get 4g theta into h cube by n pi, which is from the previous term, minus 4g theta into bracket open minus x into 2h by n pi the whole square into cos n pi x by 2h, x equal to 0 to x equal to h, minus 0 to h minus 2h by n pi the whole square into cos n pi x by 2h into dx. So now we get the equation above. We substitute x equal to 0 and x equal to h. When we do so, we get cos n pi h by 2h. So the h will get cancelled. Cos pi by 2 is 0. So that first term is also 0. The second term we are multiplying by 0. The second term is also 0. So which gives rise to the value that x equal to 0 to x equal to h, actually the entire term becomes 0. So when we do so, we have 4g theta into h cube by n pi minus 4 into 0 minus 4g theta into 2h by n pi the whole cube into, when we substitute for the third term, we have x equal to 0, x equal to h. So sin n pi h by 2h minus sin n pi 0 by 2h. So here n pi h by 2h, h gets cancelled. So sin n pi by 2, which is 1, and that sin 0 is 0. So we have 4g theta h cube by n pi minus 4 into 0 minus 4g theta into 2h by n pi the whole cube into 1. So this gives the value 4g theta h cube by n pi minus 4g theta into 2h by n pi the whole cube. So this is the first term in RHS, which is equal to 4g theta h cube by n pi minus 32g theta h cube by n cube pi cube. Now let's evaluate the second term in the RHS, which is given as 2 into 0 to h g theta into h square into cos n pi x by 2h into dx. So cos becomes sin when we integrate it. So it becomes 2 into 2h by n pi into g theta h square into sin n pi x by 2h x equal to 0 to x equal to h. So we have 2 into 2h by n pi into g theta h square into sin n pi h by 2h minus sin n pi 0 by 2h. So this becomes 4g theta h cube by n pi. Now LHS equal to Cn into h. First term in the RHS is 4g theta h cube by n pi minus 32g theta h cube by n cube pi cube. And the second term in RHS is 4g theta h cube by n pi. So substituting these values in equation 5, we have Cn into h equal to 4g theta h cube by n pi minus 32g theta h cube by n cube pi cube minus 4g theta h cube by n pi. So Cn into h equal to minus 32g theta h cube by n cube pi cube. So Cn becomes minus 32g theta h square by n cube pi cube. The h gets cancelled. So substituting the value of Cn equal to an into cos h into n pi b by 2h, we have an into cos h into n pi b by 2h is equal to minus 32g theta h square by n cube pi cube. So this becomes an equal to minus 32g theta h square divided by n cube pi cube cos h n pi b by 2h. Substituting the value of a sub n equal to minus of 32 g theta h square by n cube pi cube into cos h n pi b by 2h in v of x comma y. So, v equal to sigma n equal to 135 up to infinity a n into cos n pi x by 2h into cos h n pi y by 2h. So, this gives rise to the equation v equal to sigma n equal to 135 up to infinity minus 32 g theta h square divided by n cube pi cube into cos h n pi b by 2h into cos n pi x by 2h into cos h n pi y by 2h. Now, this is the value of v. So, substituting the value of v in the total stress function phi, we have total stress function phi equal to g theta into h square minus x square plus v of x comma y. So, the phi value becomes phi equal to g theta into h square minus x square plus sigma n equal to 135 up to infinity minus 32 g theta h square divided by n cube pi cube cos h n pi b by 2h into cos n pi x by 2h into cos h n pi y by 2h. So, now let us obtain the solution for the torsional moment T. So, the T is given as T equal to 2 into minus b to plus b minus h to plus h phi into dx dy. So, the value of phi or the equation of phi has been derived as shown in the left hand side of the screen. Now, substituting the stress function phi in the above equation, we have T equal to 2 into minus b to plus b minus h to plus h, and then the value of phi, which is a long derivation, into dx into dy. We know that the solution for torsional moment can be expressed in the generic form of T equal to g theta j. Upon comparing the terms of RHS of these equations, the torsional constant j can be obtained by solving the equation. So, now we have j equal to 2 into minus b to b minus h to h, a big equation which is phi into dx into dy. So, this is the equation for j as you can see in the screen. Now, the equation for j appears little more complicated. So, let us split it into two integrals, the first one and the second one. The first one is basically 2 into minus b to plus b minus h to plus h square minus x square into dx into dy. So, the first term now becomes 2 into minus b to plus b x h square minus h cube by 3. Lower integral is minus h and upper integral is plus h into gy. So, again we substitute the upper bound and the lower bound values. We finally end up with a value here which is 2 into integral of minus b to plus b 4h cube by 3 into dy. Again, when we integrate this value, we have 2 into y into minus b to plus b. So, this becomes 2b into 2h the whole cube by 3. So, this is the value for the first part of the integral, which is equation 1 here. And then for the second one, we have another bigger integral, as you can see here. And this integral can be again easily integrated with first with respect to dx, and then once that is done, we can integrate it with respect to dy. So, when we do so, when we integrate it first with respect to x, we have cos n pi x by 2h now becomes 2h by n pi into sin n pi x by 2h. So, we substitute the lower values and the upper values, basically the boundaries. So, now we have to focus the double integral. The first part of the double integral is to focus on the x function. So, when we integrate cos n pi x by 2h, we have 2h by n pi into sin n pi x by 2h. We substitute the lower and upper bound integrals minus h and plus h. We simplify this further, and when we simplify this further, we get the value as shown in the equation here. And then we continue to the next slide here, and we still have this values here, minus b to plus b into 4h by n pi into cos h n pi y by 2h into dy. We have to integrate this one. So, when we integrate it, we have 2h by n pi into sin h cos n pi y by 2h. This is the value that we get when we integrate cos h n pi y by 2h. Again, we substitute the values minus b and plus b. So, when we do so and simplify this further, which you can see from the slides here, it's simple mathematics, and then we take sin h into n pi b by 2h divided by cos h n pi b by 2h as tan h n pi b by 2h. So, this becomes equation 2. So, when we multiply all the values here, this 32 into 4 into 2 into 2 becomes 1024. H square into h becomes h power 4. That n cube into n, we get n power 5. pi cube into pi becomes pi power 5. So this is the constant of the equation 2. So substituting the values of 1 and 2 in the above equation for j, we have j equal to 2b into 2h the whole cube by 3 plus series function sigma n equal to 135 up to infinity minus 1024 h power 4 by n power 5 h power 5 into tan h n pi b by 2h, right? Now what we can do is that we can take this minus 1024 h power 4 by pi power 5 outside. So when we take that outside, we have j equal to 2b into 2h the whole cube by 3 minus 1024 h power 4 by pi power 5. Now series function introduced, n equal to 135 up to infinity 1 by n power 5 into tan h n pi b by 2h. So we expand this series function. When we expand the series function, we get the equation as shown on the screen here, right? So we can also do one thing. We can take 2b into 2h the whole cube by 3 as common. So we have 1 minus. Then when we do so, we get this 3 by 2b into 2h the whole cube. So because when we take this 2b into 2h the whole cube by 3 outside, we have to multiply that in the second term inside. So the second term becomes minus 192 by pi power 5 into 1 by b by h. And then there is a series function that we have already described. Now what will happen when b by h is very large? So b by h is very large, it's a thin narrow rectangular cross section. When b by h is very large or it tends to infinity, this 1 by b by h tends to 0. So when 1 by b by h tends to 0, the j value boils down to j equal to 2b into 2h the whole cube by 3. If that is not possible, we can say that j equal to 2b into 2h the whole cube into k1, where k1 is given as the value of 1 by 3 into 1 minus 192 by pi power 5 into 1 by b by h into sigma n equal to 135 up to infinity 1 by n power 5 into tan h into n pi b by 2h. Now the value of k1 depends on the function of or the aspect ratio of b by h. When b by h equal to 1, the value of k1 is 0.141, but when b by h is tending to infinity, its value boils down to 1 by 3 or 0.333, as you can see here. So for thin narrow rectangular cross sections, j equal to 1/3 2b into 2h the whole cube. Therefore, for cross sections with multiple narrow rectangles, we can simply apply this formula for not only for rectangular cross sections but also for I sections, as you can see from the picture on the right hand side. So we have an I section where the width of the flange is b1, thickness of the flange is t1, and the depth of the web is b2 and the thickness of the web is t2, so on and so forth. So this is very similar to what is given in Annexure E, page 129 of IS 800. You can see that the torsional constant is given as sigma 1/3 bt cube for open cross sections. Here the 2b equal to b sum I and 2h equal to ti. However, we need to note that this value of j is only for open cross sections and it is invalid for closed cross sections. The derivation for closed cross section we will see in the next class. Thank you very much.